Lecture 33, Brain-Computer Interfaces and Thought-Directed Combat Systems. According to the U.S. Department of Defense's updated policy in January 2023, autonomous weapon systems can be developed and fielded as long as commanders and operators retain appropriate levels of human judgment over the use of force. In practice, this means a human decision-maker must stay in the loop even as technology accelerates the engagement cycle. The last time a soldier's physical trigger pull mattered more than the soldier's intent was before modern electronic warfare made clear how fragile links can be. In Ukraine, for example, whenever heavy jamming erupts and a Starlink satellite uplink hiccups, whole units fall silent. The bottleneck then isn't lack of weapons or drones, it's the lag between a human deciding and a machine acting. That bottleneck is precisely what brain-computer interface, BCI, combat systems target. By moving the human decision closer to the weapon's trigger, without removing human control, the DoD has effectively greenlit efforts to shrink the kill chain from hand, to voice, to eyes, and now to cortex. As one analysis of the new autonomy directive notes, human judgment over the use of force doesn't necessarily mean hands-on control, it means a human authorizes and can veto, even if the system handles the mechanics. A thought-directed combat system embraces that principle. The human stays on the loop, but the loop itself becomes as tight and fast as thought. This sets the stage for everything that follows. The hardware stack for a brain-weapon interface literally begins in living tissue. The first question is where and how to tap into the brain's signals. One approach is to go invasive implant sensors directly into brain cortex, which yields high information density at the cost of surgery. The venerable UTAR array is an example, a tiny bed of nail silicon chip that spikes into the cortex to read electrical activity from neurons. Each array carries 96 electrode shanks. Multiple arrays can be combined to provide around 256 to 1024 channels of neural recording with current clinical technology. In practice, this has enabled experiments decoding fine motor signals, reach and grasp movements, even attempts to write letters by imagining hand strokes. BlackRock Neurotech, which manufactures the UTAR array, bluntly advertises its specs: 96 electrodes per array in a 4x4mm patch, 400 micron spacing, typically up to 1024 total channels in a multi-array implant. That's enough resolution to distinguish individual intended motions. But the device's size belies the challenge of putting it in the brain. Every bit of bandwidth is paid for in biology: micromotion of the electrode in tissue, scarring, gliosis around each shank, corrosion and encapsulation over months and years. The body's immune response doesn't take kindly to silicon and metal lodged in grey matter. In short, you get a rich signal from invasive electrodes, but you incur surgical risk and long-term maintenance costs in the form of gradual signal degradation and health oversight. As of mid-2025, these high-density intracortical implants remain limited to small clinical trials, but they have proven they can capture complex intentions at the cost of a hole in the skull. If open brain surgery is a non-starter for wide deployment, there are intermediate options. Surface electrodes placed on the cortex, electrocorticography, or ECG, can trade some resolution for vastly easier installation. Companies like Precision Neuroscience are developing ultra-thin, flexible ECG sheets that can be slipped under the skull but above the brain tissue, avoiding penetration. In April 2025, Precision's Layer 7 cortical interface, a 1024 electrode film about 1.5 square centimeters, received FDA clearance for temporary human use up to 30 days. These paper-thin arrays conform to the brain surface, recording local field potentials over a broader area. The pitch when talking to military planners is straightforward: you can get a 1,000-channel signal without literally sculpting into the brain, minimizing risk while still feeding modern machine learning decoders with plenty of data. By treating the implant as a temporary scaffolding to train the system and then removing it, an army could imagine equipping soldiers with high-bandwidth brain interfaces during intensive training or certain missions, then pulling the hardware out, leaving no permanent mark beyond perhaps a small burr hole in the skull that heals. The data would stay with the soldier's personal model, improving over time. This approach is already moving from science fiction to regulated reality. Precision's FDA clearance explicitly labeled the device for temporary use, exactly fitting this paradigm of use it for a month, calibrate the decoder, then take it off. The first such devices are being tested in patients as we speak. An even less invasive path rides the body's own highways, the blood vessels. The motor cortex of the brain is fed by blood vessels that a doctor can thread a catheter into. Synchron, a startup, has developed the stent road, an electrode array that is delivered via a vein run up through the jugular and into a cortical vein that sits against the motor cortex. Once in place, the stent-like device expands, pressing an array of electrodes against the vessel wall from inside and recording neural signals, all without a single slice into the brain itself. In September 2024, Synchron announced early feasibility trial results. All 6 patients implanted with the stent rode for 1 year met the primary safety endpoint, with 0 device-related serious adverse events. In other words, at 12 months in, the device caused no significant harm. The neural signals, while lower amplitude than those from a penetrating array, were stable enough to drive basic digital commands. By mid-2025, the company showed those patients using the interface to control consumer devices, an iPad tablet, a smart home assistant, purely by thought. One participant, for example, was able to compose text messages on an iPad using only the endovascular BCI, as demonstrated in August 2025. For the military, the appeal of this approach is obvious. It turns implantation from neurosurgery into an endovascular procedure. Instead of needing a craniotomy and a neural surgeon, an installation could be done by an interventional radiologist with catheter labs, resources available at major hospitals and military medical centers. As one commentary noted, the logistics of surgery is strategy, and a BCI that can be installed with a wire through a vein is a very different war plan than one that needs a full surgical suite and months of rehab. By bypassing the skull entirely, Synchron's stent also dodges many immune responses once the device's electrodes, endothelial eyes, get covered by the vessel's lining cells. The body might treat it as just another stent. The signal won't be as sharp as a UTAR array's spiking action potentials, but it might be good enough to tell a drone, go there, or to signal, fire, to a weapon. Non-invasive BCIs, those that read brain signals without any implant at all, round out the sensor options as a kind of backup or low-tier interface. Electroencephalography, EEG, from scalp electrodes can detect broad patterns of brain activity, but the skull blurs and dampens the signals severely. Still, clever paradigms have allowed even these low-bandwidth channels to be useful in constrained tasks. A classic example is the steady-state visual evoked potential, SSVEP, system. The user stares at one of several flickering symbols on a screen, each flicker at a different frequency, and the EEG readout shows a matching frequency response in the visual cortex. By picking up which frequency is resonating in the brain, the system infers which symbol the user is focusing on, effectively extracting a choice or a target from the user's mind at about 20 bits per minute in many lab demos. It's slow, but it works. Another common paradigm uses event-related potentials like the P300 signal, which spikes when the brain recognizes a rare target stimulus. By flashing many options and waiting for the telltale P300 bump, an EEG-based system can guess which item is the intended one. These methods have achieved on the order of tens of bits per minute reliably in controlled conditions. However, they do so by essentially hijacking the user's visual attention and are notoriously fatiguing. In a combat environment, imagine trying to stare at a flickering icon through smoke, sweat, and adrenaline. It's viable only for very limited actions. At best, such non-invasive BCIs could serve as a redundant yes-no channel or a means to select a target marker hands-free when conditions allow. The battlefield penalizes these tricks with harsh reality. Motion, glare, stress, helmets, and vibration all wreck the delicate control required for a person to focus and for the system to interpret their EEG. As a result, non-invasive BCIs are likely to be niche in combat, perhaps a fallback mode for when high-bandwidth implants aren't available, or for low-stakes functions like flipping through map layers or sending a quick CAN signal when silence is paramount. Even so, the military does see a role for them in certain scenarios. Being able to silently click an approval or select an option with a thought could be the difference between being detected by an enemy or not. It's telling that DARPA, as far back as 2009, invested in a program called Silent Talk to explore exactly this, recognizing EEG patterns for silent communication between soldiers. Those early experiments only captured a few words worth of brainwave patterns and required intense focus, but the goal was clear: if you can whisper with your brain instead of your mouth, you can coordinate under nose-to-nose combat conditions without ever making a sound. All these neural sensors, invasive, on the brain, in the blood, or on the scalp, produce a flood of raw data. A single 100-electrode intracortical array can generate megabits per second of signals if you sample at high rates. The research devices push this to extremes to prove what's possible. 4. instance, Paradromics reported its Argo platform could record 65,536 channels at 30 plus kHz with 12-bit resolution. That's an immense data rate, utterly impractical for a mobile warfighter but valuable to show the upper bound. In practice, operational BCI systems must drastically compress and reduce this data on the fly. The ideal design is to extract only the key features, the user's intended command, or a low-dimensional representation of their state and transmit just that. As one researcher wryly put it, you do not broadcast your action potentials over a wideband link, you ship intent as sparsely as possible. A soldier's brain signals are precious intelligence to an enemy if intercepted, and a high-volume data link is a ripe target for jamming or geolocation. So the computation layer of a BCI system has to be equal parts decoder and guardian. Good decoders can infer the user's intent quickly from noisy data. Great decoders know when not to act, when the signal is ambiguous or likely an artifact. In the context of a weapon system, this is literally life and death. The state-of-the-art in BCI decoding has advanced rapidly in the last few years, mainly thanks to machine learning and large datasets from paralyzed patients. In August 2023, 2 separate teams, one at Stanford, one at UC San Francisco, published breakthrough results in speech BCI systems. One used intracortical implants to decode attempted speech at about 62 words per minute, the other used a cortical surface electrode grid to decode at 78 words per minute, both orders of magnitude faster than previous efforts. Error rates dropped into usable ranges by leveraging language models for prediction. This was the moment neural decoding stopped being a parlor trick and started approaching the speed of natural conversation. By 2025, Stanford researchers had even begun decoding inner speech, words a person was imagining saying but not actually speaking. They showed it's possible to get intelligible output from these silent thoughts, though with a crucial caveat: it only works reliably if the system is gated by the user's conscious control. In other words, the person had to deliberately press send on their inner voice, otherwise the decoder might blurt out idle thoughts. This finding underscores a core design tenet for any combat BCI: the machine must never act on an uncertain or involuntary signal. The decoder must have a high threshold for confidence, and a bias toward doing nothing unless clearly told to do something. Quick to respond, but quick to hold fire too. On the battlefield, the radio problem is the war problem. Getting data from the brain to the weapon means hopping across multiple links: brain to implant, if any, implant to some wearable processor, processor to a radio emitter, radio over the air, air to the drone or missile or gun platform. Every step is vulnerable to disruption. And in a peer conflict with electronic warfare flying around, it's safe to assume that robust links will become fragile at the worst times. Ukraine's conflict has been a live-fire seminar on electronic interference. Localized jamming regularly knocks drones out of the sky or blinds them. Frequency hopping and agile waveforms give only brief respites before the noise catches up. Even space assets like the Starlink constellation have suffered outages and throttling that cascade to the tactical edge. Both Russia and Ukraine have shown ingenuity in contesting each other's control links, whether through brute force jamming or more subtle hacks. A thought: controlled weapon system riding on those same networks is just as susceptible. The only solution, and it's as much a doctrinal solution as a technical one, is to minimize the dependency on comms. A guiding principle for a BCI kill chain is to push as much autonomy and decision-making to the edge, on the weapon or local controller, as possible, and require only the tiniest bit of critical data from the human. Ideally, the human's brain signal that authorizes or aborts an attack can be compressed to a single bit yes, commit, or no, veto, that can ride over any low bandwidth, resilient channel. That one bit could be sent over a soldier's existing radio, a mesh network whisper, even piggybacked on someone else's transmissions if needed. If the network dies entirely, the default should be that the weapons stop autonomously firing and hold or return to base. This way, losing comms just means losing the ability for new kill commands to be issued, which is exactly how it must be if we're to keep human judgment in the loop. The Army and NATO documents on autonomous systems all stress the same thing: build in the ability to monitor and halt at any time. In practical terms, a thought-directed weapon should behave like a well-trained guard dog. It can snarl and posture on its own, but it will only bite if the handler gives a clear command, and it will release or retreat the instant the handler even slightly signals stop. Technically, this might be implemented by constantly monitoring the operator for an oops signal. Neuroscientists call them error-related potentials, ERPS. that naturally occurs in the brain when a person detects a mistake. Modern BCIs have shown you can detect these within a few hundred milliseconds and use them to interrupt an action. Essentially, the operator's brain emits a subconscious, not that, alarm before their conscious mind has even fully processed the error. A savvy BCI uses that as an immediate veto to prevent a possible friendly fire or civilian casualty incident. It's a safety net that ironically becomes more important the faster the whole system gets. When kill decisions compress to seconds or subseconds, the human can't always articulate a cancel command in time, but their brain's "oh no" signal might still save the day. Designing for veto priority, ensuring a "no" from the brain registers faster than a "yes" is not just a feature but a requirement in all the literature on meaningful human control. Indeed, NATO's Human Control Principles and the ICRC, International Committee of the Red Cross, proposals for autonomous weapons governance both emphasize that humans must be able to intervene or abort at any moment up to the point of no return. A BCI that enforces a hierarchy where veto beats commit every time is one that could actually satisfy those ethical and legal norms. At the blunt end of the stack we have the effectors themselves, the weapons. A thought-directed system means nothing if it cannot actually deliver lethal force on target quickly and accurately after the human decides to pull the mental trigger. Thus, much of the focus is on pairing BCIs with weapon systems that are already trending toward faster, more autonomous operation. Take loitering munitions, for example, those kamikaze drones that orbit an area and dive onto targets. The Russian Lancet drone has become infamous in Ukraine, with dive speeds reportedly up to 300 km per hour and warheads in the 3 to 5 kg class. It's a brutal little missile, purpose-built to destroy artillery pieces, radars, vehicles, and even tanks, with a shaped charge. When it commits to an attack, it essentially becomes a streak of metal and explosive that slams into the target before most defenses can react. Now envision a soldier with a BCI linked to a swarm of similar loiterers. The soldier isn't manually flying each drone with their mind. That's not feasible for more than one device at a time and wastes human cognitive bandwidth on low-level tasks. Instead, the autonomy on the drones handles navigation, target search, collision avoidance, etc. The soldier's role is simply to authorize the pounce. Perhaps the drones orbit in standby, and the soldier via BCI designates a particular blip on the radar or a visual feed as hostile, as soon as sensor fusion on the drone confirms the target type. Say by matching optical and IR or getting a positive ID from a target database, the system presents a quick, commit to attack, prompt via the soldier's heads-up display. A single mental click, a deliberate thought pattern corresponding to, yes, do it, and the drone dives, smashing the target in seconds. In this loop, the human decides what to hit and when to strike, the drone figures out how to execute the attack optimally. The kill chain collapses from a lengthy procedure, detect target, radio up command, verbal confirmation, pilot drone or call fire mission, etc., into something that feels almost like a reflex. See, think, attack, target destroyed. Western small loitering munitions like the Switchblade 300, in contrast to Russia's Lancet, carry only a ~0.5 kg warhead but can be launched from a tube and fly out silently for 10 kilometers. They're more like a soldier's pocket sniper than a big hammer. In either case, a BCI that shaves even a few seconds off the kill decision loop can mean the difference between hitting an enemy rocket launcher before it scoots away, or losing the opportunity. As one observer put it, the system that moves the humans, yes, into the weapon's goal line faster, with fewer clicks, fewer words, wins. And that is not theoretical. In counter-drone defense, for instance, if you can prosecute an incoming suicide drone even 1 or 2 seconds quicker, you might stop it at 100 meters out instead of 20 meters out, which could be the difference between an intercepted threat and a catastrophic blast inside your perimeter. Directed energy weapons are another obvious beneficiary of a tight human control loop. High-energy lasers, for example, engage targets, like drones, mortar shells, or missiles, by keeping a focused beam on them for a few seconds to burn through. The US Army has been prototyping a 50 kilowatts laser on a Stryker armored vehicle as part of its short-range air defense (DEM-SHORAD) effort. Early field trials in 2020 for left soldiers underwhelmed. The laser works, but it's finicky, and the Army's test office noted that deploying the prototypes to real units actually delayed formal testing because the few available systems were shipped overseas to try and get some operational data in the Middle East. Nonetheless, the technology is improving, and doctrine is adjusting with it. Lasers will likely be used alongside traditional interceptors, missiles, to handle cheap, small threats en masse, saving the expensive missiles for whatever leaks through. In a thought-directed context, Imagine an air defense operator who sees a cluster of hostile drones incoming. Normally they'd have to slew a laser turret manually or with a joystick and then engage, perhaps selecting modes on a screen. With a BCI, the operator could literally look at a sector of the sky through their visor and think, commit, and that is enough to authorize the laser to fire on any target that enters that sector until told otherwise. Essentially, carving a no-fly corridor with a glance and a thought. The physics of the laser don't change, it still has to deal with beam diffraction, atmospheric bloom, dwell time, but you've collapsed the engagement sequence to the bare minimum. Already, soldiers who tried the 50 kilowatt Striker laser in 2023-24 came back with feedback that it wasn't reliable enough to depend on solely. The Army's response in 2025 was to frame near-term lasers as just another layer in air defense, not a wonder weapon. That's realistic. A BCI won't magically fix the power and thermal limits of lasers, but it will ensure that when the laser is ready to shoot, the only delay to pulling the trigger is light speed from brain to beam. A human staring at a drone and internally pressing fire could shave a second here, 2 seconds there, and when engagements sometimes last only 5 or 10 seconds total, that's significant. In summary, the thought loop adds nothing to the weapon's raw power, but it strips away human fumbling. It turns a checklist, unlock laser, select target, confirm friendlies clear, fire, into something closer to a reflex action under human oversight, see threat, mentally click consent, laser already firing. As the Army noted, these systems will augment, not replace, kinetic defenses. Likewise, the BCI augments, not replaces, the soldier's decision, it just makes that decision travel at the speed of thought. To grasp the human-machine control logic of these systems, it helps to break down what each part does best. The autonomy, AI, does the dull and fast parts, sensor fusion, target tracking, navigation, stability, flight or aiming corrections, and ensuring safety interlocks, so it doesn't shoot friendlies or violate no-fire zones. The human does the contextual, ethical, and judgment parts, decide if a target is legitimate, pick which threat to handle first, choose to abort if the situation changes. In practical terms, as DARPA and others have emphasized, the human should only spend their bandwidth at branch points, moments of choice rather than continuous control. Picture a swarm of 10 drones loitering above a battlefield. A traditional, manual approach would require a joystick operator or pilot for each, or one operator cycling between them to give commands, far too slow if multiple threats appear. In a BCI approach, the swarm's onboard AI might automatically space the drones out, assign search sectors, and even identify possible targets. The human's neural interface presents these to the operator's augmented reality visor as simple icons, perhaps with confidence levels. The operator can then, with a quick thought, assign drone A to target tank 1, drone B to target radar 2, drone C to target vehicle 3, and so on, literally distributing the work among the machines with a series of rapid approvals. Each drone dives and attacks as appropriate, using a pre-programmed profile, a top attack-shaped charge on the tank, a fragmentation burst on the radar antenna, etc. If any target doesn't match criteria or civilians appear, the human can veto or redirect as needed, but they are freed from flying each drone and focus only on the targeting decisions. The kill chain becomes an assignment problem, not a piloting problem. Humans under stress excel at pattern recognition and prioritization, e.g., figuring out which incoming threat is the highest priority and distributing responses, whereas trying to manually stick-handle a fast drone or precisely aim a beam is better left to automation. By leveraging each side's strength, the combined system reacts faster than legacy setups. In one counter-unmanned aircraft test scenario, a soldier with a BCI could spot an incoming hostile quadcopter visually, glance at a HUD icon to classify it as foe. Maybe the icon turned red upon positive identification via friend or foe sensors and behavior analysis, and authorize an automated nearby interceptor to engage all without saying a word or reaching for a radio. Those seconds saved mean the difference between neutralizing the threat at a safe distance or the drone getting close enough to do damage. Notably, none of this is mind control in the science fiction sense. The human isn't telepathically levitating objects or directly puppeteering machines with sheer thought. It's more prosaic. The brain interface is effectively a hands-free mouse and keyboard, operating through sophisticated signal decoding. It turns out that's enough to be revolutionary on the battlefield. Silent, rapid communication between man and machine short-circuits many traditional vulnerabilities. Militaries have long dreamed of wordless comms. Recall that DARPA, silent talk, project which hoped to send EEG-based messages soldier to soldier, because silence is stealth and speed. In practice, that 2009 effort didn't yield deployable tech. Reading complex messages from EEG remains far too error-prone, but it established a goal that persists: say nothing, signal everything. The US Army also invested in a concept called targeted neuroplasticity training, which wasn't about operational comms but about accelerating learning by stimulating nerves during training to reinforce brain circuits. That program had mixed results. One 2024 study showed that vagus nerve stimulation failed to improve some cognitive task training, but again the through line is speeding up the human side of the loop. Whether it's learning 1% faster or reacting 1% faster, that can translate to survival on the battlefield. A BCI that reduces reaction time by even a fraction, say a soldier can signal an intent 300 milliseconds quicker than via voice or manual control, might give a 20% increase in effective response rate across dozens of engagements, and those margins add up in war. When these interfaces get deployed in real units, they will have to contend with the mess of real war networks. We've touched on jamming and outages. It's worth emphasizing just how tenuous connectivity is likely to be in a high-end fight. The Ukraine war shows that both sides actively and adaptively degrade each other's links. 1 minute the drone feed is up, the next it's static because a truck-mounted jammer lit up on a nearby hill. Frequency agility, spread spectrum techniques, and mesh relays can buy you a few extra seconds or create redundant paths, but nothing is guaranteed. Even the famed Starlink, which Ukrainian forces rely on, suffered a roughly 1-hour global outage on a September 2025 day, which immediately impacted frontline ops. Commanders reported that drone flights had to pause during the blackout. That was likely a technical glitch, but adversaries are certainly exploring how to cause similar effects deliberately. Chinese military writings obsess over targeting low Earth orbit satellite constellations and finding ways to take down the sky for NATO forces. For a thought-directed kill chain, the lesson is crystal clear: assume the primary network will die at the worst moment. Therefore, architect the system such that each combat element, drone, loitering munition, etc., can operate on its own for a while or revert to fail-safes if it loses the human signal. That usually means having some onboard autonomy that defaults to a conservative behavior, e.g., loiter in a holding pattern or return to base if no command is received for seconds. It also means having backup comms channels, maybe a low-frequency radio that can send a single bit at a time, or an optical IR line-of-sight link as a fallback. The mantra becomes, no AC, no fire. If the weapon doesn't receive an explicit go from a human or a positive target confirmation from sensors, it should err on the side of not engaging. Silence on the net is treated as an automatic veto, not as permission. In technical terms, the system's control plane must be built like a submarine's radio protocol: extremely low probability of intercept, burst transmissions, heavy error correction, and a mindset that the operator might be cut off at any time. The soldier's intention is not a suicide pact with a brittle network. If the network fails, the soldier's last command should default to hold fire, unless life or mission critical autonomy dictates otherwise. Power and sustainment factors are less glamorous but critically important for these systems. Any on-body or in-brain electronics are constrained by biothermal limits. You can't allow implanted devices to heat surrounding brain tissue more than about 1 degree Celsius above normal. International safety standards and FDA guidelines enforce conservative limits on absorbed energy. Practically, this means implanted BCIs must run on milliwatts of power, not watts. Neuralink revealed some of this in their 2019 disclosures, citing a single-digit milliwatt budget for their implants chip. An independent academic thermal modeling found that around 75 milliwatts on a skull-mounted unit was the max to stay under 1 degree Celsius rise in tissue. In short, anything high performance has to be either extremely efficient or push the heavy computation and communication to an external pack, like a helmet module or a chest unit, to keep the heat away from the brain. This is why many designs use the implant purely as a sensor, encoder, and send data to an external device that does the number crunching and heavy comms. The soldier might have a small ruggedized processor on their vest or helmet that takes the neural data and runs the decode algorithms, only pinging the implant with tiny pulses of power and receiving small packets of spiking data. Wireless charging or hot swap battery packs would be needed for implants if they are to stay in for days. Current prototypes often need daily recharges, which is fine at home but a logistical factor in war. Imagine platoon medics having to ensure everyone's brain implant is charged each night. On the platform side, the drones, the lasers, etc., power is also a rate limiter. A 50 kilowatts laser shot for 2 seconds uses 100 kJ of energy. if running off a vehicle's engine. It needs a beefy generator and capacitors, and it might take many seconds or even minutes to recharge between shots. A thought-controlled system doesn't eliminate those constraints. If anything, it adds its own overhead because now you also have to power the BCI link and devices. So system engineers do a lot of math to ensure the BCI's communications are as sparse as possible. If you naively streamed raw neural signals, you'd waste power and bandwidth. Instead you compress down to that 1-bit command or few-bit vector. The math is uncompromising, as one analyst put it: if you transmit raw features, you die; if you transmit only approvals, you live. In sustainment terms, the BCI becomes just another piece of gear with its own consumables, battery life, spare parts for headsets, extra implant arrays if ones degrade. Intracortical arrays, for instance, are known to lose some electrodes over time. The first year sees the sharpest drop, perhaps a 10 to 20% loss of signal quality as a body reaction smooths out the tissue contacts, then a plateau. Endovascular devices might fare better long-term. The vessel wall can incorporate them, providing stability. Surface films are explicitly temporary, 30 days currently. This means a military unit employing BCIs must plan for rotation and replacement, swap out or re-calibrate implants periodically, carry spares for external modules, and factor in that not every soldier's brain link will be 100% all the time. It's analogous to night vision goggles. You bring backups and you assume some will break or batteries will die at the wrong time. Just as importantly, you train for failures. Soldiers will need drills for what to do when your brain link goes down mid-mission. Maybe that's when they revert to hand signals or voice, or when autonomy is allowed to widen its parameters until comms are restored. The key is to avoid a single point of failure where a glitchy BCI renders a unit combat ineffective. Robust design will include things like dual redundant sensors, perhaps 2 separate neural signals confirming an intent, or a cross-check between brain command and eye tracking to ensure they agree. It will also lean on architecture minimalism. If one channel gets corrupted or jammed, the system fails safe rather than doing something dangerously unpredictable. For example, if the HUD, heads-up display, data is suspect or flooded with duplicates, the system might require a direct brain confirm and a secondary sensor confirm before acting, so a hacker can't trick both at once. It's the old adage, 2 is 1, 1 is none, applied to neural commands and sensor fusion. The industrial base is already aligning to build many of these pieces, whether or not the military has formally asked for them. Elon Musk's company Neuralink gets a lot of public attention. In 2024 they got FDA approval and implanted their first human with a wireless, high channel count BCI, showing that even a private venture can move fast in this space. The patient, a 30-year-old man with paralysis, recovered well and was reportedly able to control a computer mouse cursor by thought after the surgery. Neuralink's design emphasizes fully implantable hardware, no wires sticking out, and has pushed innovation in electrode threads and battery systems. Interestingly, Neuralink also had to publicly acknowledge difficulties in mid-2024 when some of the ultrafine electrode threads in that first patient's implant detached from the target area. Their algorithms had to adapt to lost channels. They eventually compensated and still demonstrated functional use, but the hiccup was a healthy reality check. On the other end of the spectrum, Synchron's less aggressive but safer endovascular approach continues to rack up steady, drama-free progress. Their trial updates read like cardiology follow-ups, hitting safety milestones on schedule. Precision Neuroscience, as mentioned, got a clearance to start using their surface film in humans for short durations. Paradromics, a quieter player, completed the first in-human test of its high-channel, Connexus, platform in mid-2025 during a planned neurosurgery for epilepsy, a temporary implant that recorded neural activity successfully, proving their massive channel approach isn't just PowerPoint. And numerous university labs, Stanford, UCSF, Berkeley, etc., have turned decade-old neuroscience experiments into robust decoders that function when a person is actually moving, sweating, and under stress. The Government Accountability Office, GAO, delivered a report in 2024 that, far from hyping brain tech, was quite cautious, raising points about regulatory pathways, data privacy, and human factors integration. Rand Corporation analyses similarly highlight that while the potential is huge, there are many hurdles: how to train troops on these systems, how to manage the data, how to deal with psychological and social impacts of effectively turning soldiers into cyborgs. The big defense primes, Lockheed Martin, Northrop Grumman, etc., have been mostly waiting for clear military requirements before jumping in with full programs. But signs of movement are there. Anduril Industries, a newer, software-first, defense company, took over the Army's troubled IVAS goggle program from Microsoft in 2023 to 2025, signaling a shift to more agile development. In early 2025, the Army formally approved transferring the $22 billion IVAS contract to Anduril and its partners. Anduril has openly said they view the advanced headset as a platform for beyond line-of-sight perception and integrating with AI, which could naturally extend to brain interface control in the future. The headsets already include eye tracking, thermal imaging, and augmented reality HUD capabilities. A BCI tie-in would essentially press the glass from inside the skull, as one commentator quipped, meaning the soldier's thoughts would interact with the digital overlay directly. The Army's latest IVAS prototypes, version 1.2, have improved comfort and reduced nausea issues that plagued earlier versions. They are still not beloved by soldiers, but they are trending towards something fieldable by the late 2020s. That is exactly the kind of platform a BCI would piggyback on. It supplies power, compute, comms, and a visual interface. All the BCI has to do is insert commands into that pipeline and perhaps read some info from it. Given the involvement of players like Anduril and even Meta, Facebook's parent, which Anduril partnered with for some AR tech, one can see an ecosystem forming where tech and defense companies converge on soldier-worn electronics that fuse vision, communication, and brain input. The legal and ethical rails for this technology are being laid even as prototypes hum in labs. On the military side, the autonomy directive we discussed, DoD Directive 3000.09, provides a baseline, yes to autonomy, no to unaccountable lethal force. Congressional Research Service updates in 2025 reiterate that U.S. policy is to pursue these advanced systems but always with human judgment at the critical point. NATO, too, via its Parliamentary Assembly and various strategy documents, has embraced language about meaningful human control and responsible AI in defense. Meanwhile, international advocacy groups in many nations, especially in the UN discussions on lethal autonomous weapons, pushing for clearer rules. The ICRC in 2021 publicly called for a new legally binding instrument to prohibit certain types of autonomous weapons and strictly regulate others. In April 2025, Human Rights Watch renewed the pressure for negotiations on a treaty to ban killer robots that lack human control. These discussions directly impact BCI-enabled weapons. A brain-linked drone swarm might satisfy the letter of human in the loop, because a person is giving final approval. But skeptics will ask if it satisfies the spirit. Is the human really in control, or just rubber-stamping AI decisions at machine speed? To address this, designers can build in features that create an audit trail of human inputs and system states, essentially being able to show, in hindsight, what the machine believed and what the human decided at each step. This could be crucial not only for internal accountability, e.g., investigating an errant strike, but also for convincing allies and oversight bodies that the system is used lawfully. Interestingly, neurotechnology has its own emerging legal concept, neurorights. Chile led the way by amending its constitution in late 2021 to protect the rights of citizens over their brain data and mental privacy. It basically says your thoughts can't be accessed or altered without consent, and any technology dealing with brain data must respect your mental integrity. The OECD, a club of developed nations, adopted a 2019 recommendation that organizations innovating in neurotech should follow principles like safety, privacy, and human dignity. This might sound abstract in a military context, but it has real effects. If a country like the US wants to field brain links for soldiers, it will have to ensure it's voluntary and that the data isn't misused. For example, no covert monitoring of soldiers' thoughts beyond what's needed for the mission. In practice, the military may have to obtain explicit informed consent from service members to use a combat BCI, much as they do for certain experimental drugs or vaccines. And they would need policies to prevent misuse, like prohibiting using the BCI to record anything other than specific command signals, and maybe even giving soldiers an off switch, or ability to remove the device when not in combat. Lawyers and ethicists have pointed out that a BCI could become a surveillance tool if misapplied. For instance, commanders could theoretically try to monitor if soldiers are attentive or fearful via brain metrics. That is a dystopian road that would destroy trust. Smart program design will wall off neural data so that only the narrow, necessary intent signals are transmitted, and nothing is stored long-term beyond operational necessity. Commanders should not get a dashboard of Soldier A's stress level in real time, because that's not far from reading someone's mind or emotions without consent. Instead, the tech should treat brain data with the same protections as medical information, need to know, and with consent. Chile's example shows that these neural rights ideas are gaining traction. Spain, for one, has also discussed similar protections. By 2035, any nation deploying neural interfaces at scale in their military will likely have had to answer to these norms, whether via formal law or simply public expectation. The bottom line: a brain-computer interface that amplifies a soldier's intent while embedding a hard veto and an audit trail is not just a technical asset but a legal one. It helps prove that the system remains under control and isn't violating fundamental human rights. Where does this lead by 2035? Likely to lots of quiet integrations rather than splashy standalone cyborg units. By the mid-2020s, all the pieces for basic thought-directed weapons are in motion. HUD visors like IVAS that can display targets in a soldier's field of view, drones and loitering munitions that are already semi-autonomous, and neural interfaces entering early human use. By 2035, we can expect specialized units or testbed squads using modernized headsets that incorporate neural approval for certain actions. A platoon leader might approve a drone's attack profile with just a blink and a thought confirmation, instead of grabbing a tablet. An artillery officer could silently reprioritize counter-battery targets as new enemy radars light up, feeding the fire control network faster than voice commands could travel. A naval officer on a ship's deck could assign sectors to an array of laser turrets and give a mental engage to swat incoming drones or mortar rounds, all while their hands are still on other tasks. These aren't sci-fi scenarios, they are extensions of tech already demonstrated. For instance, in 2018 DARPA revealed that a paralyzed volunteer flew a simulated F-35 jet using a bidirectional neural interface. In a separate DARPA trial, another volunteer controlled multiple simulated support drones in formation via a brain link. Those were simulations with highly trained subjects, but they proved the concept. As actual hardware improves, the fielding will probably start small, maybe one thought-controlled drone per squad as a pilot program. The doctrine that emerges will be procedural ruthlessness, not giving every grunt telepathy, but systematically shaving every unnecessary second and keystroke from the kill chain. One guiding question will dominate design reviews: when the link dies and the HUD goes dark, does everything fail safe? If the answer is no, back to the drawing board. By 2035 the winners will be systems that integrate seamlessly, not ones that require constant pampering. The gear will still be clunky, expect plenty of wires, batteries, bulky goggles, but if it works when it matters, troops will adapt to the clunkiness. Between 2035 and 2050, we'll see the true normalization of these technologies. Endovascular and surface BCIs will likely become routine procedures in the civilian medical world for things like stroke rehab or assistive communication. That means when the military wants to use them, it's not an experimental surgery, it's something any major hospital can do. The vision is that an infantryman could be fitted with a temporary cortical interface at a medical battalion or even forward surgical station, use it for a 6-month deployment, then have it removed without permanent effect. Over these years, head-worn displays, the HUDs, will improve too. Today's narrow field of view and motion sickness issues will give way to lighter, broader displays that soldiers accept as just another piece of kit. The Army's IVAS spiral updates suggest by late 2020s we'll have 60-degree FOV, much better ergonomics, and general acceptance after they iron out the worst bugs. By 2040 or so, we might consider those high-tech goggles akin to the adoption of night vision in the 1990s, at first specialty, then ubiquitous. Lasers and other directed energy weapons should go from prototype to actual inventory items in this period. The Army is already talking about an enduring high-energy laser program for steady acquisition. Swarm drone control will likely be baked into standard battle management software by then as well. By analogy, once upon a time radar data and SAM control were novel, but by the late 20th century they were integrated into air defense doctrine. The same will happen with swarms. They'll fold into combined arms tactics, with perhaps some swarms controlled by AI and some directed by human in the loop for more sensitive decisions. A thought-controlled interface will simply be one more way to input commands amid this, alongside voice commands, touchscreen clicks, etc. Training pipelines will adapt. New recruits might get introduced to neural devices in boot camp the same way they learn to handle radio equipment. Daily calibration of one's BCI could become as routine as zeroing your rifle or doing comm checks. There may even be mental veto drills, where soldiers practice overriding automated suggestions using their brain signals, building that reflex so it's rock solid under pressure. By 2050, the systems that succeed won't be the flashiest, they'll be the ones that keep working when everything goes wrong. That means tolerance for network loss, for dirty sensors, for a groggy or stressed operator. The measure of merit will be how boring it is. If a thought-directed weapon becomes just another normal part of operations, that's success. From 2050 to 2075, the line between blood and silicon, human and machine, will blur further, but not in the cliched way of unhinged killer robots or full transhumanism. Rather, improved hardware and clarified laws will make the trade-offs clearer so we can choose wisely. By this time, fully implantable systems might be so efficient in power use and signal processing that wearing one is low maintenance. Perhaps a special operations team member opts for a permanent implant because it gives them continuous high-bandwidth control for complex missions. Imagine controlling a cluster of microdrones in a subterranean tunnel system. You'd want the best interface possible. Meanwhile, regular infantry might mostly use endovascular or on-surface interfaces that are periodically refreshed, just part of the gear turnover. The concept of a kill chain might morph into a dozen micro-decisions rather than one big red button press. Instead of fire and forget, it's observe, permit, in a rapid cycle. Weapons themselves will largely be the same killing mechanisms: fragmentation explosives, shaped charges, kinetic slugs, lasers, maybe high-power microwaves, but guided with greater coordination. The advantage will lie in shortening the distance between thought and force while keeping it controlled and lawful. The side that can do that reliably wins the hours more often than it loses them, as engagements stack up. In plainer terms, conflicts may still drag on for years, but within each skirmish or confrontation, having a faster, tighter human decision loop will tip the scales in those countless small encounters that aggregate to victory. By 2125, a century from now, this will all seem ordinary, almost invisible. The hardware will have receded from view, literally perhaps, with implants so small and wireless that you can't tell who has won. The concept of neurorights will likely have settled into established law, much like privacy laws eventually caught up to digital communications. It's very plausible that by then brain data will be protected similar to how communications are protected, at least in democracies: audited access, consent required, and strict penalties for misuse. Autonomy in weapons will also probably be governed by a handful of straightforward rules encoded in all systems, like an equivalent of the Asimov's laws but legally enforced via tamper-proof software. There will always be humans authorizing lethal force, not because the AI couldn't make a targeting choice, but because we choose to retain that moral agency. Humans can understand context and contradiction, for instance, recognizing that a target could be both an enemy combatant and someone's father, or that blowing up a certain building might win the battle but lose the war by enraging the local population. A brain can hold those nuances in a way a policy written for a machine cannot. So by 2125, humans will still pull the trigger, but maybe the trigger is now a mental click in the recesses of their own mind. The interfaces might even be silent, no obvious gestures or spoken words, just a squad moving through a battle space and weapons responding almost as extensions of their will. That doesn't mean war becomes a video game or that ethical constraints disappear, quite the opposite. The big battles of the 21st century to control AI and neurotech use will, hopefully, result in widely accepted constraints embedded in these systems. Perhaps every lethal BCI will have to incorporate multi-factor authentication in a sense, a *** liveness check to ensure the operator is who they say, some unique brain reflex that can't be spoofed. Maybe even a two-person rule for really big actions, requiring two separate operators to mentally confirm a high collateral attack, and an automatic black box recorder that logs every engagement decision in a format a review board or war crimes tribunal can later examine. If those sound burdensome, remember that by then the tech might be so fast that even with those safeguards, the loop is still faster than it is today with a purely manual system. Two soldiers thinking, yes, within 1 second of each other could launch a heavy weapon, whereas today that might require a whole chain of command. Future weapons themselves, by the late 21st century, might appear deceptively boring. Loitering munitions, for example, will likely diverge into two main categories: small, cheap, disposable ones for platoon-level fights, and larger, coordinated ones for higher-level strikes. The small ones, 2 to 3 kilograms warhead, 20 to 30 minutes endurance, tens of kilometer range, will be ubiquitous. Every squad might carry a few, launched from tubes or drones, quietly cruising and then slamming into targets like generators, vehicles, or enemy positions. The large ones will work in packs. Imagine 4 to 8 drones working together on one target set. One blasts the radar, another takes out the optics, another carries a shaped charge for a hardened bunker, another drops submunitions to keep repair crews away. A human operator in 2075 isn't micromanaging those wolf packs, they're just selecting which pack attacks which target set and giving the go. Your fault is not their steering wheel. Your fault is the assignment, as one expert succinctly put it. Directed energy systems by then, lasers, high-power microwaves, will likely be deployed wherever it makes sense, warships, large land vehicles, fixed installations, as routine defenses. They'll be fully automated in mechanics. No human can aim a laser better than an AI at that point, but with humans setting constraints, no fire zones, priorities, and pressing the equivalent of engage when certain conditions are met. High-power microwave, HPM, weapons, which can disable electronics across a swarm, might complement lasers for those dense attacks inside a kilometer or two. The BCI's job with these will be the same as ever, make targeting and deconfliction faster than a shout and more precise than a hurried trigger finger, then get out of the way. In essence, the brain link will become a quiet enabler that nobody thinks twice about, much like radios are today. They're just there. Countermeasures in the late century will co-evolve. Already we've seen how simple tactics can disrupt complex systems. In our era, strobing lights in the frequency range of an opponent's BCI could theoretically confuse their SSVEP interface. If you know they're using 13 Hz flicker to select targets, you might flash random 13 Hz patterns in their environment to provoke false responses. We expect early mind-machine systems to be hit by these kinds of spoofing attempts. But defenses will mature. Designers will enforce that the BCI only listens to trusted visual stimuli, like the system will ignore any flicker that it didn't generate itself, perhaps by coding it with a cryptographic signature in the timing jitter. They'll include photonic watchdogs to blank out or filter dangerous frequencies from the display if there's a risk of an adversary exploiting them. And they'll give the user a manual abort gesture that's super easy, maybe a deliberate jaw clench or tongue click, which is detected by EMG sensors to immediately cut the interface if something feels wrong in what they're perceiving. On the electromagnetic side, an enemy might try to zap the BCI with an EMP-like pulse or just saturate the area with noise so the neural sensors can't pick up signals. Again, none of this is new in concept. Think of World War II radars getting buzzed by chaff. The counter is to harden the hardware, shielded cables, robust analog front ends, and to have algorithms that require persistent signals over multiple time frames before acting, so a single blip of interference can't trigger a false command. If the adversary gets really close, like physically close enough to try using a transcranial magnetic stimulator to scramble your brain signals, well, that means your perimeter was already penetrated. At that point, your BCI isn't your biggest worry, your situational awareness and good old marksmanship are. Indeed, decades of neuroscience have used strong magnets to induce currents in the brain, TMS therapy. But doing that in combat against someone's head is not exactly a practical battlefield tactic unless you're within arm's reach, and if you are, you might as well use a bullet. It's a fringe scenario. More broadly, though, we anticipate electronic warfare to look less like sci-fi hacking and more like power management contests. The side that can pump out more jamming power, and simultaneously keep their own sensors and comms powered and coherent, will dominate local engagements. BCI systems, if designed lean, low emission, low bandwidth, edge processing, inherently have a smaller footprint to detect or disrupt. They talk less, so there's less for the enemy to hear or jam. They also default to independence, edge autonomy, if comms drop. Therefore they may prove quite resilient in practice, not because they can't be jammed, but because there's not much to jam. One-bit commands don't offer a large attack surface, and because even if jammed, the system just waits or falls back to safe mode instead of going haywire. By 2075, what started as exotic countermeasures, flicker attacks on neural interfaces, direct neural jamming attempts, might have already come and gone, replaced by more banal ones, e.g., deepfake visuals to confuse targeting AI, energy barrages to overwhelm any and all electronics. The key in countermeasures will remain the same: keep human and sensor confirmations independent and design every kill decision to require concurrence of multiple channels. That way, an enemy has to fool the AI and the human in the same moment to cause a misfire, a much taller order than fooling one or the other. Looking further into the late 21st century, training and organizational culture will likely adapt to fully embrace human-machine neurointegration. By 2050 to 2075, new soldiers might undergo routine calibration and familiarization so that using a BCI is second nature, much like using a radio or night vision goggles became standard. We might see an evolution of physical training to include cognitive endurance, ensuring troops can maintain focus to drive BCIs for longer periods, and recognizing signs of cognitive overload. Already we know that pupils dilate and blink rates change as mental workload increases. Future HUDs might display a cognitive load meter, derived from eye tracking or the BCI signals themselves, and intelligently slow down how many prompts or decisions it asks from the operator when they're near overload. Perhaps if a soldier is in the middle of controlling a drone swarm and simultaneously getting shot at, the system will automatically refrain from asking them to authorize a low-priority action, and might even lock out lethal commands if it detects their attention is too fractured, preventing accidents. Military doctors and psychologists will also have to watch for cognitive doping, the temptation to push soldiers to enhance their mental throughput with stimulants or brain modulation, so they react faster and keep that veto sharp at all hours. There could be analogues to today's rules on pilots using go, no-go pills, amphetamines to stay alert, sedatives to sleep. Overuse might fry an operator's judgment, even if it amps their reaction time. So rules and recovery periods, near rest akin to crew rest, will be instated, maybe something like, no one can be on continuous neural control duty for more than X hours without Y hours of rest, similar to how flight crews are limited today. The human edge will persist and even become more prominent precisely because machines will handle more of the rote and rapid tasks. Humans will be valued for what they uniquely contribute: context, restraint, and creative problem solving. An AI might identify a target and propose a shot, but a human might recall, wait, our intel suggested that compound could hold civilians, abort. Those kinds of judgment calls, the when not to pull the trigger, will remain squarely on human shoulders. A century from now, wars will still ultimately be decided by human intent. Technology will just mediate how directly and quickly that intent translates to action. A likely quiet revolution by 2125 might be in command structures and initiative. When junior leaders have the tools to make split-second decisions that currently would require higher headquarters approval, because now they can see and act so fast, militaries may need to decentralize decision-making further. If every weapon in your sector can be queued in milliseconds and every sensor feeds directly to those at the edge, you won't have time to ask a general, may I fire, for each shot. So initiative will push downward, a trend already seen in modern warfare, but this could cement it. Future command might punish delay more than disobedience, within reason, because failing to act in the 1-second engagement window is a greater sin than taking an imperfect shot that higher-ups wouldn't have chosen in hindsight. A well-designed BCI network could provide a record, which two operators approved this strike, what data did they see, etc., to ensure accountability, but trust will be placed in those forward operators to use their fast loop wisely. At the strategic level, this means nations fielding these technologies must train and trust their soldiers' judgment deeply, because those soldiers will be effectively fighting at the speed of algorithms but with human lethal authority. It's a double-edged sword. They can win skirmishes in the blink of an eye, but a mistake also happens just as fast. Hence the insistence on ethical constraints built in. Faster does not mean reckless, if done right. It should mean the opposite, faster at stopping when conditions aren't right. It's important to state what this future won't be. It won't be clean, or safe, or push-button easy. BCI-enabled warfare is still warfare. You're still sending explosives into metal and flesh, just with less lag. If anything, making it easier and more reflexive to pull the trigger in a tight situation raises the bar morally. We have to ensure the ease doesn't translate to casualness about killing. The closing of the gap between thought and force is something to be handled with extreme care. The best case is it saves friendly lives and prevents some collateral damage by making responses precise and timely. The worst case is it removes what little cognitive buffer remains between anger and violence. The design philosophy emerging, thankfully, leans toward caution, require deliberate commits, require positive stops, and engineer the systems to default to not engaging unless clearly told otherwise. The last safeguard is always a disciplined human mind. No machine can make war moral, that's on us. The hope is that these thought-directed systems, by keeping humans in the loop yet speeding up their interaction, will actually prevent the nightmare scenarios of runaway AI slaughters. We will still have a human brain, messy, emotional, responsible at the point of execution, just now they'll have a supercharged interface to express their decisions. The final paradox is that to maintain humanity in warfare, we are going closer to the brain than ever before. As one war scholar put it, the future worth building is one that keeps the human's judgment closer to the trigger, without erasing it. A well-designed brain-computer combat system does exactly that. It shortens the distance, in time and translation, between a soldier's intent and the weapon's action, yet keeps that distance safe and lawful, meaning under control and accountable. If that cannot be ensured, then such a system should not be deployed at all. The coming decades will test whether we can pull this off, marrying human ferocity with machine speed in a way that amplifies the former without unleashing the latter unchecked. The technology is racing ahead, the challenge now is to harness it so that timely never overrides wise.